Good day, guys, and welcome to Intellect Academy. Welcome you all to today's channel. Today's channel we're going to be solving a question on centrifugal pumps. So we have a question here on the board. I think this is going to be the last example on centrifugal pumps. Okay, now let's go to the question. Okay, now let's say the centrifugal pump lifts water from the well and discharges to the atmosphere. So it's from the well to the atmosphere. It discharges the water, and we said that one of the functions of pump is to what? In normal cases where gravity will act on fluid, let's say the fluid is flowing from the well to the atmosphere. In cases like that, gravity will act on those fluids. So the work of the pump is to move, which is to increase pressure to move out the fluid. In this case, I say it's always liquid. So now the pump has the following operational data. Let's say number one, they have what? The static suction lift. So we're going to write our given parameters. So first of all, we're given our static suction lift, which we know will signify as what? Zx. We're giving this as 2.5 meters. Then they say we have the static discharge head. We will also signify, if you don't understand these symbols, you can go down to our last video so that you can get a clear understanding on what we're doing here. So we have ZD, which will signify as what? Static discharge head, as 14 meters. We have our velocity in suction pipe, we will say is the velocity at inlet, which is signified as Vx. So we have Vx to be 1.02 meters per second. We have the velocity in delivery pump, which is the velocity the fluid or water leaves the pipe or the pump. We call it Vd, which is 8.4 meters per second. So we have an overall efficiency, which will signify as this, of 80%. We have our dynamic losses, and we said that those they are mostly due to frictions. So we have our dynamic losses, which we have the loss in the suction pipe and in the delivery pipe. So we signify our dynamic losses as HLS for suction. We have 1.2 meters. Then we have our for delivery we have HLD. We signify this as 5.6 meters. Okay, now they say what we to determine. They say determine the suction and discharge head, then the total system head. So they say we should determine the suction head, the discharge head, and the total system head. In our last video, we gave an expression for the suction head, the discharge head, and the total head. We said that the total head is the discharge head subtracted from the suction head. So we're going to give our values for this. So we're going to find our first one, which is I. So we're looking for the suction head. So we're looking for suction head. So we know that the suction head, which is H, S, is going to be equals to Zx, which is the static suction head, plus the pressure over rho G, plus the velocity, which is Vd square over 2G negative HLS. And I told you that this HLS will be negative anytime it deals with what? The section. Is that understood? Now we know that for the delivery head, we said that the delivery head is HD, is given by ZD plus PD over rho G plus V. Okay, this is Vx, take note, over Vd square over 2G plus HLS. And we said that these parameters here, I told you, take note that this will be positive while this will be negative. So we also said that the total head is given by this expression. The total head is given by H, capital letter H is equals to HD minus HS, which we will also know that it was equals to HD negative HS bracket plus PD negative PS over rho G all in bracket. Then we had plus bracket VD square negative VS square over 2G. Then we had plus, now take note, we're having negatives, we're having plus H. Okay, this will be D. Take note, this will be D, HLD. Very important, we're having HLD. Now, there's a negative here and we're subtracting by a negative, so it will automatically affect this. This will become plus HLS. Okay, now we are going to solve this example. So first of all, let's say we should calculate the suction head, which is the case is HS. So we're looking for this parameter, which we know that this is HS equals to ZX plus PX over rho G plus VX square over 2G negative HLS. Now take note, let me give you a small diagram that illustrates this operation in the centrifugal form. Let's say we have a pumping system like this. So we have our pump. Let's say this is our pump. Okay. So we know that this is the datum line. Let's call this the datum line. So from here to the datum line, this is the discharge. Let's call this from this datum line to this point. Let's call this the suction. So the pressure here we'll call the PX, the velocity to use the flow is VX, the head will be called ZX, this will be called ZD. So this is the pressure will be here, which will be PD, the velocity which will be VD. So now take note, this is like a small diagram that I'm trying to illustrate the question because it's flowing from the well to the atmosphere. So let's call this the atmosphere, just to make things kind of understandable. So this is the atmosphere, it flows out to the atmosphere. Now take note, at this point of inlet, gravity will be equals to 0. So we're having our gravity to be 0. Take note, our gravity is 0 and our pressure is 0. So we're having, at this point, we're having Px equals to PD. Take note, since it's discharged to the atmosphere, PD is equals to Px, which is equals to 0, and gravity is equals to 0. So if we do that, we're going to have Hs equals to Zx plus, we're having 0 over 0 here, plus Vx square over 0, negative HLS. We know that this is going to cancel out. So we're going to have Hs is equals to what? Zx negative HLS. Now take note, at this point, your Zs is below the datum line. So take note, since it is below the datum line, it will be taken as negative. It is very important in problems involving centrifugal pumps and in a number manometers, you understand, in pressure or piezometers. So take note that your Zs, your suction head, in cases like this will always be negative because it's below the datum line. So we are having this to be HS. So our suction head is what, 2.5. We're going to call it negative 2.5 because it's below the datum line. Very, very important. So we're having this, we're having negative HLS is what? 1.2. So we're having 1.2, which will result to what? Negative 2.5, negative 1.5. This is going to give us negative 3.5 meters. So this is our suction head. In this case, our suction head is given by 3.7 meters. So we have our what suction head HS to be what negative 3.7 meters. So now let's look for what our delivery head given by HD. We know that HD is given by this expression ZD plus px over rho g plus v squared d over 2g positive HLD. Now take note, I told you earlier that in the case of this, it is always positive. It is positive always. Take note of that. In cases of this, it is always positive. Now take note, we are having this to be 0. Take note of that. Now at this point, which is at this point, or this point of flow, which is the discharge side of the centrifugal pump, we are having that G is not equals to 0. So at this point, G is equals to 9.81 meters per second square. Take note of that. And take note, this is not negative because of it is above the datum line. So this is the datum line. It is above the datum line, so be taken as what? Positive. So we have our HD given by ZD is equals to what? 14 meters. So we have 14 plus our velocity, which is 5.6 square over 2 times 9.81 plus our HLD is what? Okay, our velocity, sorry, our velocity is 8.4 meters per second. So we have our velocity to be 8.4 meters per second. Then we have our answer, which is our HLD to be what? 5.6 meters. So this will amount to 23.2 meters. So this is the value of our HD, which is the delivery head. Take note of that. So now under this question, they say calculate the suction head. We just calculated it. We got negative 3.5 earlier. So we just calculated also our discharge head, so which is the HD. So our discharge head HD is equals to 23.2 meters. Now let's say calculate the total head. Now the total head, our total head, big letter H, is equals to HD negative HS. Where we know that our HD was what? 23.2 negative. We had this as what? Negative. So we're having negative brackets negative 3.7. So this will be equals to, we have 23.2. Now negative will be what? Plus 3.7. So we're having 23 plus 2, 23.2 plus 3.7. So this will amount to 26.9 meters. So take note that this is our total head. So our total head is given by 26.9 meters. So the next question is talking about the power required to drive the pump. Okay, now we have to calculate the I part of this question, the power required to drive the pump. So we have to look for what? I, the power required to drive the fluid, drive the pump, required to drive the pump. So to drive the pump, so we're looking for that power. Now take note, from efficiency, we know that efficiency is equals to power required to impact the fluid, impact the pump, all over what? Power required to drive the pump. So from here you can see that we have the power required to impact the fluid. So let's call this power required to impact the fluid. Let's call it power to impact. So we have power impact. So we have power impact over power drive. So we're going to make so power to impact is given by this expression, the total head multiplied by gravity. Very, very important equation in the course of this. So we have our total head, we calculated our total head to be 26.9. Then our gravity, of course, we know is 9.81. So when we do that, we're going to have our value to be 26.9 multiplied by 9.81. So this will give us an expression which is 263.88 watts. So this will give us an expression 263.88 watts. So now we can make power to drive subject formula. So we have power drive, which is to drive the pump, is equals to power to impact, which is power impact over efficiency. Okay, so we're having this, which is the power to impact, power drive to be. Now the power to impact is given by 263.88 over. Now efficiency is 68%. So our efficiency is 68%. So we're having this multiplied by 100, this multiplied by 100. So we're having this multiplied by 100 over 68. Now, so we're going to have our power to drive the pump given by an expression which is 388.1 watts. Take note that this is the power to drive the pump. So from here we know that the power required to drive the pump is 388.1 watts. We have to calculate our net positive suction head at cavity inception. So we have to calculate III, which is the third question. We have the net positive suction head, which is represented by NPSH. Take note that it is equals to HS negative the vapor pressure over rho G. Now take note, because they gave us that we have cavity inception, we cannot solve this using this method. Take note, they gave us what? Assume the dimensionless specific speed to be 0.64. And take note that we had our formula for, in our last video, we had our formula for NSS, which is the specific suction speed. In this case, it is quite different, but because of this dimensionless speed, specific speed quantity, we are going to use another formula which is different from this because of we have cavity inception. If they gave us to calculate the net positive suction, in this case, we are going to use this formula because we are giving the pressure of this vapor, which is 1.2 times 10 to the power 4 Newton per meter square. So we are going to use this formula, which we say that for dimensionless, so we have for dimensionless speed, we have that our NS S is equals to, it is less or equal to our bracket NPSH over H raised to the power 3 over 4. Now take note, this is multiplied by 2.88. So we have 2.88 bracket NPSH. I think this is the formula here. Okay, now so take note, this formula is what we're going to use to calculate when we have a dimensionless speed or specific speed. It's very important to know this formula. So we are going to make our NPSH subject formula from here. So what we do is, first of all, is to divide both sides by 2.88. So we have NSS divided by 2.88 less or equal to NPSH over H. H signifies the total head, 3 over 4. So what we'll do here is to take the inverse of the power of both sides. So we will do that. We're going to have bracket. We have NSS over 2.88 raised to power 4 over 3, which is the inverse of 3 over 4. We have less or equal to what? Bracket NPSH over H. So we have 3 over 4 multiplied by 4 over 3. So this will cancel this will cancel this. You're going to be left with 1. So automatically our formula for this, we have our NSS over 2.88 all 4 over 3 is less or equal to our NPSH over H. Now what we'll do next is to move this to the other side, which is cross multiply. We're moving this H to the this left hand side. So we're having H multiplied by the NSS over 2.8 raised to power 4 over 3 less or equal to NPSH. So what we'll do now is to rewrite this, bringing our NPSH to this other side. The inequality sign is going to change. So now if we have NPSH, take note, if this value is less or equal to the NPSH, when we are rewriting this, we're going to say that if this value is less than this, that means this is greater than this. So we're going to say that this is going to be greater than H bracket NSS over 2.88 bracket 4 over 3. Is that understood? So when we do that, we're going to have our NPSH is going to be greater than, we have our total head. Our total head was given by 26.9 meters. So we have 26.9 bracket. We are given our NSS, which we have 0.64. So we have 0.64 over 2.88 bracket 4 over 3. Take note that our formula for the NPSH will be equals to, so we have our formula for NPSH. This is equals to 3.62. Now the NPSH will occur at this point. Take note that if the NPSH is greater or equal to this, that means the minimum value of the NPSH. Take note, the NPSH, which is the minimum value, will be equals to 3.62. Now take note that this inequality sign gives us the description of what I said earlier, that it is greater or equal to 3.6. It can never be less than 3.62. So therefore the minimum value as cavity inception is equals to 3.62. Now we are going to calculate for the next part, which is the maximum permissible suction lift. So now take note, we can calculate the maximum permissible suction lift from our NPSH value. Now take note, our NPSH value can be, which as we said earlier, it is equals to HS negative PV over rho G. It is very simple that we know this expression. So this can be expressed as ZX plus PX over rho G plus VD and VX square over 2G negative HLS negative PV over rho G. Now take note that at this point, it's very okay that we say that the velocity is 0. Now take note, this is our value for the NPSH. So we can collect like terms. So we're going to have ZX. Now when we bring these two together, we're going to have plus Px over Pv over rho g negative HLS. So our NPSH is equals to what? Plus, so we have Zx plus Px over, take note, this is very important. Take note that at this point we are looking for what? The maximum permissible suction lift. It is very important that at this point, this Px is going to be P0. That is going to be the pressure of atmosphere. Take note, it is very important. At this point, Px is going to be Po. So we are having a case like this where Px is equals to Po, which is equals to the atmospheric pressure. So this is the atmospheric pressure, which we know that it is given by 1.01 times 10 to the power 5 Newton per meter square. It is very important to take note of this. So you can take note, we're going to make Zs subject formula. So we have Zx is equals to NPSH negative. So when we bring this to the other side, we're having negative bracket Px, which is in terms of Po, negative Pv over rho g plus HLS. It is very important to take note that this is our Z max of X, which is the maximum permissible suction lift. Now our NPSH, we calculated it earlier, we got it to be 3.62. So we have 3.62 negative. We have our pressure to be 1.01 times 10 to the power 5 negative. Take note, they give us our vapor pressure to be 1.2 times 10 to the power 4. So we have this as 1.2 times 10 to the power 4 over our density, which is density of water, is 1000 multiplied by gravity, which is 9.81. Now plus our dynamic head loss, which we got this to be 1.2. Now when you do an arithmetic operation here, you're going to see that our Z maximum permissible suction head lift is equals to negative 4.25 meters. So it is very important you take note of all these examples, because it's very important you understand points like this. Now take note that our last question we calculated here, which is here we have the maximum permissible suction lift. This is the maximum permissible suction lift. Now we said that the suction lift is from the point of inlet to the datum line. This is where we see our suction head. So the maximum permissible lift from the well to the datum line is going to be negative 4.25. Take note that we knew that our suction lift earlier was 2.5. This is the maximum value of that suction lift. It is very important to take note of this. So this is the end of sample problem involving centrifugal pumps.